Hi, folks. We're going to skip section 4.84. That's a very short section. We're not going to use it, though. And I'm going to do today two sections, 4.85 and 4.86, and that will cover the rest of section chapter 4. Actually, I don't know if it's 4.86. It could be 4.10. I have to check. I retract what I said. I just checked. We are covering sections 4.9 and 4.10 today, but we're not going to cover the last part of 4.8, which I believe is 4.84. Okay, so that is the story. Let's get started. So 4.9 is about sums of random variables. So what do I mean by that? So for example, if you have X and Y are random variables on the same sample space, you can form a new random variable Z, which is X plus Y, for example. An example of this might be, let X be the outcome of a roll of a red die, and let Y be the outcome of a roll of a green die, and then X plus Y is the sum of the dice. Okay, so what I'd like to do is determine what the expected value of a sum is. And before I do that, I want to introduce a proposition that's mentioned in the book, which goes like this. So let's let X be a random variable on the sample space. And let's let the PMF, let P of be the PMF, the probability mass function of this random variable. So then the proposition says the following: if we want to compute the expected value of X, we can rewrite it in the following way. It's the sum over all elements S of S of X of S times P of S. So it really does look like a weighted sum in this, weighted by the random variable. So let me give you a proof. Maybe the proof should be in a different color. Let's make it in green. Okay, so let's set x1, x2, x3, etc. These are all real numbers. This is the set of values of x. The set of all values that x can take. So that's a subset of the real line. And let's set for each index k, s sub k, it's the set of all s in S such that x of S is equal to the value x sub k. Okay, then what do we conclude so far? Then we've partitioned S into S1, S2, union S3. These are all pairwise disjoint events. Okay, so then what is the expected value of X? The expected value of X, by definition, is the sum of xk times the probability that X is equal to xk. That's how we defined it way back when, and they were summing from k equals 1 to infinity. But that's the same thing by definition as the sum over k of xk times the value of the probability of the event S sub k, right? Because S sub k is the preimage of X sub k. This is by definition of Sk. Now, what is the probability of the event Sk? Well, let me first rewrite this, the sum over k, xk. The probability of sk is an event, so that's a union of outcomes. Which outcomes? It's the sum, it's the probability of all s's, where s is an element of sk. So I'm just, probability of sk consists of a bunch of elements, and the probabilities add. And here p, I'm using little p now, because I'm using the PMF. Okay, and now, what is that? That's the same thing by the definition of what x sub k is. It's the sum as k goes from 1 to infinity of x of s. Oops, I didn't write this correctly. I think I'm going to go back to black ink. It'll be clearer if I do it in black ink. This is the sum of the following. So xk is the value of elements of sk under the random variable. So this is the sum over k, the sum over s in sk of xk. But what is xk? Xk is x of s times p of s. But now this is a double sum. This is exactly the same thing as the following single sum. It's a sum over all a, over all s, I should say. S and s of x of s times p of s. And so we're done. Okay. So why did we do this? Well, we did this really for the following corollary. If x1, x2, etc., maybe you have n of them, are random variables on the same sample space, of course, then we can form the sum of all the random variables. I goes from 1 to n, and we could ask what the expected value of the sum is. And the answer is the expected value commutes with sums. It's the sum, I goes from 1 to n, of e of xi. And the proof is very simple. So let's set z equal to the sum of the random variables. I goes from 1 to n. Then what is the expected value of z? That's the same thing as the sum, s in s, of z of s times p of s, the probability mass function at s, and this is by the previous proposition. Okay, but what is z of s? Z is the sum of the random variables. So this is the same as the sum over s in s of x1 of s plus x2 of s dot 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 plus xn of s evaluated at p of s. And now we break it up into n different sums. So this is the sum of over s in s of x1 of s times p of s plus dot 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 plus the sum s in s of xn of s times p of s. But this is the same as e of x1 plus e of x2 dot 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 plus e of xn, and that's what we had to show. Okay, so that wasn't that hard. So here's an example. Suppose we have n fair dice. So let xk be the outcome after tossing the dice of the kth die. So then the expected value of the sum of all the xk's, k goes from 1 to n, is the sum over k of the expected value of xk. But that's the sum over k. What's the expected value of rolling a die? We actually compute Who did that? That's 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by, we average, so we get 7 halves, it turns out. That's what we got. So this is, k, and k is going from 1 to n. So there are n copies of 7 halves, so it's 7n over 2 is the answer. Okay. So that's all I want to cover in this particular section, 4.9. So we're done with 4.9. The next thing to cover is 4.10. Okay, so let's recall what the cumulative distribution function. 4.10 is about the cumulative distribution function. Recall that what this is it's the function f of x is given by the probability. So you have a random variable x. And it's given by the probability that x is less than or equal to x. That's how we defined it. And here are the properties. So, property 1, f is non-decreasing. Oops. So that means that, for example, f of a is, if a is less than b, then f of a is less than f of b, less than or equal to. If a is less than b, then f of a is less than or equal to f of b. 2, property 2. If we take the limit as, why is that true? Because you're getting larger events as x increases. So if b is bigger than a, the event x less than or equal to a is smaller than the event x is strictly smaller and contained in the event x is less than or equal to b. The limit as x goes to infinity of f of x is the probability, of course, that x is less than infinity. But the probability x is less than infinity, of course, is a probability of 1. Last property that's key here is that the limit as x goes to minus infinity of f of x, well, that's going to be equal to 0 because the event x is, you're getting smaller and smaller events going to, this is like the limit. This here is the same as the limit of as x goes to infinity of x is by definition the probability as x less than or equal to x. So, oops, I'm not saying this right, but these events are getting smaller. These events shrink as x goes to minus infinity. So this has probability of 0. Okay, so those are the 3 basic properties that we need to know. And I want to do an example. The example is in the book, and it requires some calculation. So I put on the whiteboard the example from the book that's on these pages. I think it's called example 10A in this section. And here is a cumulative distribution function, and to the right, I've actually graphed it. And what I'd like to do is, the problem is to compute the following quantities. The probability that x is strictly less than 3. Oops. Well, there are 4 parts, and I'm just going to do one part at a time. So let's compute the probability that x is less than 3. Well, the way to do this is to relate that to the cumulative distribution function. And one way to do that, what does it mean for x to be less than 3? This is the same thing as the following. It's the same as the probability that x, oops. It's the same thing. Suppose we, instead of x less than 3, we look at x less than or equal to 3 minus some very small number 1 over n. where n is going to infinity. You see, as n goes to infinity, 1 over n tends to 0, and x being less than or equal to 3 minus 1 over n for all n is exactly the same as saying x is strictly less than 3. And we can indicate that in the graph here. These are points that are getting closer and closer to 3, but never touch 3. Okay, so this is the same quantity. Now, the advantage of doing this is that this is the same thing as the limit as n goes to infinity of f of 3 minus 1 over n, by definition of the cumulative distribution function. Okay, so what is f of 3 minus 1 over n if n is large? That's a number slightly less than 3. If you look on the graph, you get a value of 11/12. So the limit, so you get 11/12 as the answer to that part. Let's look at part B. Part B is the probability that x is exactly equal to 1. How do we compute that from the CDF? What you do is, this is the same thing as the probability that x is less than or equal to 1 minus the probability that x is I didn't say that. Yeah, strictly less than 1. But this is exactly the same thing as f of 1, that's the probability x is less than or equal to 1, minus, now we have to express this strict inequality by, use the same trick we use in part A. This is the limit as n goes to infinity of f of 1 minus, I didn't say that right, limit as n goes to infinity of the probability that x is less than or equal to 1 minus 1 over n. And that's the same thing as, what is f of 1? F of 1 is by definition 2/3. So it's 2/3 minus the probability, minus the limit as n goes to infinity of f of 1 minus 1 over n. But what is the value of f of 1 minus 1 over n for all n? It's given by the formula here. It's x over 2, so it's going to be given by 2/3 minus the limit as n goes to infinity of 1 minus 1 over n divided by 2, because it's x over 2. And this is going to be 2/3 minus a half. And because 1 over n is going to be disappearing, and then that gives you a value of 1/6. That's the answer to part B. Let's do part C. That is the probability that x is bigger than a half. Well, we can use the complementary probability as 1 minus the probability that x is less than or equal to a half. Notice that the strict inequality gets replaced by a non-strict inequality when we do the complementary event. And this is the same as 1 minus f of a half. But f of a half, if you go to the graph, is 1/2 over 2. So it's 1 minus a half over 2, which is 1 minus a quarter, which is 3/4. Okay, last part is to calculate the probability that 2 is strictly less than x is less than or equal to 4. Well, this is the same thing as the probability that x is less than or equal to 4. Well, you got to get rid of the stuff that's less than or equal to 2. So you have to subtract that off. But this is f of 4 minus f of 2. And from the graph, you see this is 1 minus 11/12, which is the same thing as 1/12. And there you have it. So we have now completed chapter 4, at least the stuff I wanted to cover in chapter 4. So I wish you all a good weekend.